So, we are on the fluid mechanics part of the subject. So, previously we talked about pure substance. Such a material will demonstrate internal pressure. P arising from, well, this is a kinetic theory model that elementary particles are moving all the time, even when, well, the bulk of the fluid could be stationary or in motion, but at the particulate level they are in a state of movement and they will bounce off both real and imagined surfaces, that change in momentum being the cause of a force distribution on the surface, which is expressed on a unit area basis as pressure. So, force being newtons, pressure would be Newton per meter square. So, if there is a surface, particles are bouncing off that surface, giving rise to a force distribution. So, that is indicated by a pressure P. So, by convention, the unit normal and pressure are oppositely shown in opposite directions. That means pressure is positive when it is compressive. So, this is the notation that is used. So, that for an elemental area ds, the elemental force is written as PdS in terms of magnitude, n in terms of direction with a negative sign. Okay. So, the notion of pressure in a, well, it is actually a pure substance. We now take it forward to a fluid medium. So, matter, broadly speaking, is composed of solids, liquids and gases. Liquids and gases together are termed fluids. To contrast a fluid medium from a solid, we carry out, this is quite common in the subject of mechanics, classical mechanics. So, if I want to know a person's character, I can do it in many different ways, but all of them will involve perturbing that person, okay, push that person, and if he laughs it off, then you say, he has a good sense of humor. If he comes back fighting, then you know he is an aggressive character. Similarly, in materials, we try to understand that object by subjecting it to a test. This test is in the form of our perturbation is a force, and we look at the response. So, this mindset will be used quite consistently in the domain of mechanics. A fluid medium, when subjected to a shear stress. So, shear stress is a kind of a perturbation, a special kind of perturbation that would act parallel to that surface. So, pressure is normal to the surface, it is along the unit normal, shear is along the surface. So, you will notice that these definitions bring into discussion a chosen surface. Okay. So, that is to say, if you have a beaker containing water, you have to analyze let us say the lower surface or the vertical surface. These are independently analyzed. Okay. So, when you isolate these portions of the surfaces, you are using the notion of a free body diagram. So, going back to a fluid medium. Fluid medium as opposed to a solid is one that cannot withstand shear stress, however small. So, what happens? What happens is it is set in motion. So, there are several ways of saying the same thing. Shear stress will generate non-zero velocities in the fluid medium. Alternatively, if velocity is 0, like I said, beaker containing water, just keep it here, water is at rest or oil is at rest, air could be at rest, liquid mercury could be at rest. Shear stress in such a medium is 0. Okay. So, no shear stresses. Shear stresses will set the fluid in motion. Alternatively, if velocity is 0, shear stresses are 0. So, the subject of fluid mechanics by and large deals with fluids in motion. So, shear stresses are always there, but our initial part of the subject has fluid statics. So, if you look at fluid statics, which is chapter 2 of our textbook, shear stresses are 0. So, if you think of a small element in the body of fluid, a small element, so, on AB, the unit outward drawn normal is outwards and pressure will act this way. Here it is POA, this way it is POB. Now, the governing equation for forces acting on a small element in the body of the fluid would be that sum of all external forces is 0. Now, I am not showing. So, in this element is under static conditions. Now, sometimes the word hydrostatic is also used, but the word hydro indicates water. It could happen in air also or any other fluid. So, shear stresses are 0 for this element. So, these are the only forces acting on it apart from its own weight. So, let us say we carry out a force balance. So, it will be, let us say this angle is theta, okay, then you can readily see that PAB times AB times cos theta will balance POA times OA. So, AB cos theta is OA. So, you get POA equal to PAB equal to POB up to the weight of the element. Now, the weight of the element, now we are doing a calculation in 2 dimensions. So, in the third dimension, let us say it is unit distance. So, how much is the weight? It is OA times OB divided by 2. What is the area? Half base into height. Yeah. OA OB divided by 2 times 1 times density. Okay. So, we cancelled off, if you remember, OA. So, that means the weight compared to pressures, which are finite quantities, weight is of the order of the size of the element, which is taken to be small. So, in this calculation, weight will not play a role when you do calculations at the elemental level. So, this result you might have studied in your high school is also called Pascal's law, which says that for a fluid at rest, pressure is independent of the choice of the plane. Just 2 minutes ago, I said to discuss pressure, you select a plane, but any plane you select at a point, this elemental volume is representative of a point coincident with its centroid. Now, this point is not a geometric point, it is a point to be interpreted in the framework of continuum that we discussed last time. So, it could be maybe 1 nanocube while you are doing a calculation on the human scale. Okay, so, this is an interesting result called Pascal's law. So, let us do a similar calculation for a column of liquid which is not elemental, it is a finite column with a circular cross section of area A, and let us say this height is h. So, this is a liquid column that is chosen here. In the beaker, you take a column of liquid and carry out a similar calculation under static conditions, no shear stresses. Now, at the top, it is atmospheric pressure. Now, let us set up a coordinate system with the surface being z equal to 0, and at z equal to capital H, this is how you indicate pressure. So, this is pressure at z equal to h. Okay. And now, carrying out an equilibrium calculation. This element is at equilibrium. If the body is at equilibrium, every part of it is in equilibrium. That means, forces are 0 in every direction. So, forces are 0 in the horizontal direction, and in the vertical direction, sum of all external forces. Why sum? Because there are multiple forces, one at the surface, one at the depth z equal to h, and third is weight. So, you can immediately see that P at h minus P atmosphere multiplied by area A will be equal to the weight, which is rho g a h. So, this a will cancel off. So, you get P at h equal to P atmosphere plus rho g h. So, going back to the beaker, this is one of the walls of the beaker. You have to excuse me a little bit because I am getting used to this system. So, not able to draw a vertical line. That is a vertical line. Let us see if I can try again. So, this is the right wall of the beaker. So, starting from the surface, pressure varies. So, this h can be anything. It is any, if you think of, if you replace h by z, that is a linear variation in pressure with respect to z. So, it is a linear variation starting from P at atmosphere to P h at the base. So, as you go deeper into the liquid, that's we had a liquid. So, it could be a fluid. As you go deeper into the fluid, pressure continuously increases and is balanced by the weight. So, on a large scale, of course, weight is important, but at the elemental scale, it plays a small role. Now, you have to reconcile our class discussion with what is given in the book. I think the book uses the z coordinate to be vertically upwards. So, if you do that, let us open a new page. So, if you have z vertically downwards, then P z is equal to P atmospheric plus rho g z. But if you set it up this way, you have to change the sign of z. That means, as you go deeper into the liquid, z will be negative for a coordinate system where z is upwards. So, now you can write the differential form of this equation. Sometimes the differential form becomes useful. So, instead of going all the way up to the atmosphere, you can consider an element. So, it will be P at z and P at z plus delta z. So, that kind of treatment will give you dP dz equal to rho g. So, if you integrate, you will get this expression. The right hand side is a little more general because it allows for rho to change from point to point. Now, g also can change from point to point, but in this course we will neglect variation in g. Yeah? Please, you may be you might have used g equal to 10 meter per second square. Please use g equal to 9.8 or 9.81 meter per second square, not 10. Huh? Similarly, you might have used water density equal to 1000 kg per meter cube, but if the data is given, use it. Air density, these numbers, even though it is there in front of you, just remember it. Air, I think, is around 1.2 kg per meter cube. And be careful about units. So, with z pointing upwards, you will have dP dz equal to minus rho g to be integrated with respect to a point where you know the pressure. So, usually we think we know the atmospheric pressure. So, that can be a point of reference. Now, speaking of the atmosphere, atmosphere itself is a body of fluid. So, it will also satisfy the same equation. Okay. So, to get atmospheric pressure, you have to integrate this equation over from the surface of earth where the experiment is being carried out to outer space. Okay. So, rho changes quite a bit over this distance. If you put that rho in, you will get atmospheric pressure. Okay. But we keep saying human scale. So, suppose I am looking at a beaker containing water, the change in atmospheric pressure around the beaker is negligible. That column is so huge, the changes are very small. So, we think of atmospheric pressure also to be constant for the discussion in this class. In this class means in this course, not just today. Okay. So, all around the beaker it is the same atmospheric pressure. So, it is quite common to define a quantity called gauge pressure which is P minus P atmospheric. Okay. So, that means the gauge pressure corresponding to atmosphere is 0. This is advantageous because if you have let us think of the same beaker problem and you want to find the force acting on one of the walls. So, the wall is exposed to atmosphere on one side and liquid pressure on the other side, but liquid pressure has a P atmospheric in it. But these two you can quickly show will cancel off, which means you can set P atmospheric equal to 0 for the purpose of calculating the force acting on a surface. Okay, so, this differential form is useful if density changes with the depth of the liquid column, with the depth of the fluid column. Okay. So, I think there are some questions where it says oil is floating on water. Okay. So, you have density varying in the vertical direction. So, except that it is piecewise constant. So, you set up the integral. So, let us say the second equation, you can write P H minus P atmospheric equal to integral 0 to H with a negative sign rho g dz, where P atmospheric so here at z equal to, so I should have said well, let us say if h is equal to z, the integral is 0. And as you go down, the value of h is negative, right. So, you are going down and this integral will be rho g of minus h if rho is constant with a negative sign. So, it keeps increasing. Okay. Now, if you have a 2-layer problem, then you split the integral first over the top layer and next with the bottom layer. If rho varies continuously, that you have that functionality you have to put in. So, there are some consequences. So, you notice that for a liquid or a fluid at equilibrium, fluid including liquids and gases. So, under hydrostatic conditions, pressure varies with the depth. The next consequence is pressure varies only with the vertical coordinate. The vertical coordinate is aligned with the gravity field. It does not vary, pressure does not vary across. So, another way of saying the same thing is, you might have heard liquids find their own level. Why? Because atmospheric pressure is constant. Okay. So, that level also has to be a constant. Okay. So, we use this idea in many applications. One such application is manometry. Let me give you the configuration where the calculation has to be carried out. So, these could be two chambers A and B. Let us say they are filled with gas. Okay, now, gas density is much smaller than liquid density. So, in some calculations, you might say, I neglect gas density. So, you will see that you will arrive at a point where it is rho liquid minus rho gas. So, you may approximate it as rho L, but if you do that approximation, show it. Okay. You say you have to write in your answer sheet rho L minus rho G, let us say, is approximately rho L equal to whatever value. Okay. So, let us say A and B are vessels filled with gas, and you connect them with a glass tube, and you have this glass tube is like a U tube. Initially, it has, let us say, mercury up to a certain level, and initially the mercury level being a hydrostatic problem, the levels in the two limbs will be equal, and when you connect them, then depending on the magnitudes of A with respect to B. So, the pressure here is P A, pressure here is P B, and the way I have shown it, P A is greater than P B. So, it pushes the liquid column to one side, and this difference in levels is H. So, the question is to relate pressure A to pressure B in terms of H. So, this is manometry is a measurement procedure where you determine the pressure difference. Barometry does absolute pressure measurement relative usually to vacuum or any other standard, measures absolute pressure. Manometry measures pressure difference primarily. So, question is relate P A and P B in terms of H. So, one possibility is you start with A where the pressure is P A. Now, when you go in the vertically downward, these limbs, these are all at the so called human scale. So, the U tube might be about this big. Okay. So, when you go down, the pressure will slightly increase from A to, let me call this point 1, I will call this point 2. When you go from A to 1, it is a slight increase in pressure because of hydrostatics that we may neglect because it is a gas. Okay. So, then at point 1 pressure is A, P A. Now, you go across, this is a mercury column. If you reach this point 1 prime, pressure is still P A, and then you go up, pressure starts to decrease. So, by the time you reach point 2, it is minus rho L, this L is liquid, just to distinguish from gas, I am calling it rho L G H. You have reached point 2. So, this will give you P 2, which practically is equal to P V. Okay, so, but suppose A and B were filled with another liquid, let us say water, okay, whose density is not very small, much smaller than mercury, but still not small. Why mercury? Why is mercury used? What is the advantage of mercury? First of all, it is non-volatile. Yeah? Huh?
Large differences can be negated by small lengths of mercury.
Very good. Density of mercury is very, very high. So, if delta P is large, still rho L is large, so this H will not be very large. Okay, if you use water, then you might go to some research labs and you will see such manometers which are 3 meters in height. But with mercury it comes down. But the problem with mercury is it's corrosive and it's not very safe. So, people try to avoid the use of mercury. Of course, this is modern day manometers tend to be electronic in design, a lot more compact. So, you replace the liquid medium by, let us say, a piezoelectric transducer that will convert pressure difference into charges and hence voltage. The whole thing is very compact. So, so, if the density of the fluid in A and B, of course, those fluids can also be different. Then this expression, if it is the same fluid, then you have to subtract out that F is fluid in A and B. Okay. In case of a gas, that rho F is negligible. So, it is an example of manometry. So, let us look at an example of force calculation. We could go back to a beaker containing water, but I think in the book they have an example of a dam. See, this beaker containing this human scale is not that narrow. It goes from a beaker or it could go from a liquid drop all the way to a dam containing water, followed by, I am saying dam burst in a very casual manner, it is not desirable. So, the human scale, you can imagine the oceans, atmosphere, these are all very large. So, what is the outer limit? So, that outer limit is reached when probably some relativistic effects start showing up. So, you should be talking of light years in terms of distance and masses that are a million times that of planet Earth. So, the human scale is enormous. Okay. Just trying to say that this analysis, even though it neglects particulate, does not neglect, it factors it in through a new set of variables like density, pressure and temperature. Later we will see quantities like viscosity. It approximates particle level behavior, but the human scale, once properly set up, all models on the human scale are applicable over vast dimensions of space and time. Now, the core of physical laws on the human scale, they all stem from Newton's laws of motion. So, Newton plays, so it is also called Newtonian mechanics, continuum mechanics, classical mechanics, Newtonian mechanics, they are all interchangeably used. Okay. Later we will see that Newton also had a very important role to play in the context of fluid flow. So, we talk of Newtonian fluids. So, that way Newton is right at the core of this subject. So, force calculation, so let us think of a dam. See, this inverted triangle is used to indicate free surface. So, below the inverted triangle is water and above is atmosphere. So, this right hand side is really speaking a wall, okay, and below the wall is a gate. This gate may slide up and down. Suppose water level becomes enormous, very high, then you have to raise the gate so that you allow for some water to flow. So, if you have seen Ganga Barrage in Kanpur, you will realize that they use gates to allow for flow of water, and whatever flow is stored upstream. So, there could be a net flow from left to right, okay, but we are looking at the static configuration where the gate is closed. The body of water is stagnant. Many things can happen. You raise the gate and then there is some flow, or there is some earthquake and the entire body of water shakes. Maybe there is rainfall and then that sets the fluid body in motion. There are winds and there are waves on this body of water. So, all these can happen. But we are looking at a stationary configuration. We used to say, well, civil engineers will design this brickwork, but now all engineers have to be familiar with it. So, to design that brickwork, you will have to know the forces acting on it. Okay. So, does the wall have sufficient strength to withstand the force? So, you have wall properties, you have fluid properties. To find the force from the fluid side and apply it on the wall. So, that will take you into a combined fluid solid, you may call it interaction problem. But right now, let us say this AB is the gate and you want to find the force acting on AB because of this body of water. So, AB could be 1 meter while the entire body of water can be 10 meters, in some extreme cases could be 100 meters. So, even over 100 meters, atmospheric pressure will not change very much. Okay. So, if you are going to find force acting on AB, so the overall there is a pressure variation from top to bottom. So, at the top it is P atmospheric, and then it decrease as you go down, the pressure increases. So, this will be P atmospheric plus rho g z, where now z is vertically downwards. Okay. And if it is minus rho g z, if z is pointing upwards. So, at point A, let us say we set P atmospheric equal to 0, because you are going to find the total force acting on AB from the right hand side, which is exposed to the atmosphere, it is atmospheric pressure. So, those two will cancel off, and you can start, this is point A, this is point B, and you can start with, let us say this is H1 and this is H2. So, Z equal to H1, Z equal to H2 as measured from the top. So, over A B, you have a variation from rho g H 1 to rho g H 2. Okay, so, this is the pressure distribution over A B. Now, this is from the water side, and from the other side it is atmospheric that we have cancelled off. So, on this diagram, on this free body diagram of AB, we are showing forces in the horizontal direction. Of course, there will be reactions at A and B if point B, if the gate is in contact with, depends on the nature of contact. So, there are reactions at A and B which I have not shown. I am only doing a calculation for the force arising from this body of water. So, you may wish to represent this pressure distribution in terms of an equivalent force F. So, you remember it was PdS, and we had a negative sign and unit outward drawn normal. So, now we are showing F with the knowledge of the direction in which it is going to act. So, you can forget about time being, for the time being forget about the vector notation in scalar terms. So, you have to go from A to B, rho g z, rho g dz, rho g z dz, because this pressure is rho g z. Okay. So, it is equivalent to saying you consider a small element dz, force acting on it is p z, p as a function of z dz, and you integrate from A to B. Why A to B? Because your z is oriented downwards. And so, here at A, Z A is H 1 and Z B is H 2. So, the force acting on the gate A B is this quantity. What are the units? Newton per meter. So, this is also a 2D calculation. We have taken the gate to be 1 meter normal to the plane of the blackboard. Okay. No, not, or I should say whiteboard. This is whiteboard. Okay. So, the units are Newton per meter. And the second quantity you would like to determine is the point of application of this force. So, if it is at a distance h from point A, now that is up to you, you can choose to define h from the free surface. But let us say you want to locate the point of action of this force F, and let us say it is a distance h from A, then F times h will be equal to, you can balance moments and write integral A to B rho g z dz times, this is force times the momentum. Okay, and from this equation you can find h. So, in this see, I think in the book there are several problems where it comes up with closed form expressions. For example, this force F, you will realize is just the area of that trapezium, is it not? So, you can even without carrying out integration, you write the formula of the trapezium, area of the trapezium. Similarly, you can come up with this point of application of h. Okay. So, that would correspond to the centroid of the trapezium. So, you can use geometric results that are available elsewhere and solve these problems, but it is always useful to go through this integration route, because this rho g z assumes rho to be a constant. What if rho is not a constant? So, suppose it is fresh water floating on salt water and you have a gate over there. Okay. So, just for generality, it is better to go through the integration approach. And carry out all the necessary calculations. So, I hope you got the problem sheet for the tutorial tomorrow, and sure enough it has a small mistake. Sorry about that. So, I will send you a slightly revised, corrected, hopefully corrected problem sheet as soon as I go back to my office. So, please work with the new version. Oh, you know the mistake? What? In the fourth question, the figure shown, the drawing shown is incorrect. So, I will make that correction and send it. I have made that correction, I will send it to you. So, please work with the new problem sheet. Now, frequently you will require density, viscosity, quantities like that. So, the table of properties has also been, excuse me, see at the start of the course I will say gentlemen. Let us see if I am able to use that phrase at the end of the course. So, gentlemen and ladies and gentlemen, sorry about that. Please carry that table of properties, calculator. Now, there are many graphs. Later, at least for 3-4 lectures, you will be dealing with charts. Now, and it is a log scale, you won't know how to locate and how to read the value. So, you need a scale to read the chart. Carry a scale with you, okay, and also carry this problem sheet. It will be easy for you to discuss in the tutorial. Okay. So, tomorrow is a tutorial. There are 2 problems dealing with manometry and 2 problems dealing with force calculation. Now, can you do all four? Now, that's okay. Even if you do one each, that would be a good starting point. Okay. So, any comment? Of course, it's a huge class. Not everybody can comment, but it's very important. I can respond. So, I hope my voice continues to remain audible. If not, you will have to sensitize me. That's one. Second is, I am hoping to improve my handwriting. Okay. Otherwise, my handwriting is all right. Here. So, I am also toying with the idea of writing on a sheet and flashing the entire sheet in one shot. And I was told it's not desirable. So, what do you think? That's essentially the PPT mode. This becomes too quick. So, I'll try writing on it. Yeah, Balamurugan, any comment? Okay, so we wind up. Thank you very much. I will do ORS, yes. That's because you registered late. Huh? Then you have to, I'll comment on it on Friday. Yeah. Keep trying, keep trying. It's not a perfect system. So, in due course of time, it will become all right. It's Newton per meter. I mentioned it. Units are Newton per meter. Per meter is normal to the plane of the blackboard. I understand. Yeah. It will get correct. No. They will correct it.